So far we have been discussing acids and bases, and all those acids and bases, the acid-base reaction takes place in water. However, we have paid little attention to water itself. We have said that water is an amphoteric substance because it behaves as an acid when it reacts with bases, and it behaves like a base when it reacts with acids. And so something we have not said is that water itself has an equilibrium. So pure water, without adding any other acid and base, creates a little bit of the hydronium ion and the hydroxide ion because water reacts with itself. So if this one were to be the base and this is the acid, this would be the conjugate acid and this would be the conjugate base. This equilibrium is largely displaced to the left. However, it is an equilibrium, and there is in pure water, without adding anything else, there is a certain amount of hydroxide and hydronium ion. So if this is, how do we know this certain amount? This is an equilibrium, and the equilibrium constant K, it's called Kw, and this value, the Kw, is 10 to the negative 14, so very small. This is why we say that this equilibrium is largely displaced to the left, to pure water. So the expression for the equilibrium, the Kw, is products over reactants. However, something that we're going to do is, because water in aqueous solution, its concentration is mostly constant, we're not going to include it. So here there should be, we're not going to do that, okay, because the concentration of water is pretty much constant. So we're just going to assume that it's a pure liquid. We do not need to include it in there. Actually, if you calculate the density of water is 1 gram over liter, if you convert grams into moles, you will see that pure water is 55 molar. 55 molar is a number that's way larger than any other molarity that you will use in this course. So we consider 55 molar of pure water constant. We don't need to worry about it. Okay, so something that it may be good to know is, well, what is the concentration of hydroxide, hydronium ion and hydroxide in pure water? Pure water where we do not add anything. We can set up an ice table, and in this case, if the ice table is set up, we can just do it right here. So two waters will react to give OH negative and H3O plus. We said that initially, sure, this is 55 molar, but we're not going to worry about it. So there's going to be a certain amount here. Well, initially, if we do it right, it's 0. In equilibrium, there should be a certain amount X and another certain amount X. This value, Kw, is equal to these two concentrations, which is X times X, which is X squared. This Kw is 10 to the negative 14. This is X squared. This means that X is 10 to the negative 14 root square, which is 10 to the negative 7. So there you go. This is why in pure water the concentration of hydronium is 10 to the negative 7 molar, and the concentration of hydroxide is 10 to the negative 7 molar. Okay, in pure water. This will change, however, when we add other substances, because this constant needs to hold true. This constant needs to still be 10 to the negative 14. So let's see some of those examples. What happens to the concentration of hydronium and hydroxide when we add, for example, if we externally add 0.1 molar of a strong acid? If it's a strong acid, what you think you're adding 0.1 molar, you're actually adding 0.1 molar of the conjugate base and 0.1 molar of the hydronium ion. So let's build the ice table, and to figure out, the objective here is to figure out what are the concentrations of hydroxide and hydronium when we have added a 0.1 molar of a strong acid. Well, initially I have, this is pure water, I have 10 to the negative 7 molar of hydroxide, but notice that initially I have added 0.1 molar of the strong acid, therefore of the hydronium ion. So when I'm adding products, this is going to go to the left, therefore it'll disappear a certain amount, let's call it negative X, for both hydronium and hydroxide. So we can set up this, we can set up the equilibrium equation. Notice that I'm going to do an an approximation here, I'm gonna say that 0, 1 plus 10 to the negative 7 is pretty much just 0, 1, because it will be 0.10000001. Okay, so pretty much we can say that this is 0 compared to the 0, 1 that I just added. So kW is 10 to the negative 14, and it's going to be 0, 1 minus x, 10 to the negative 7 minus x. If you solve for x, this x didn't look like an x. If you solve for x, you're going to find out that x is this weird number. So if you find that OH negative is 10 to the negative 7 minus x, you subtract this, what you obtain is this value. In other words, the hydronium was 10 to the negative 1, and OH negative is 10 to the negative 13. Notice that these exponents add up to negative 14, which is the actual equilibrium constant. So there is a much faster way to do all that if we do not spend a single amount of time considering the initial concentrations. So let's do it very fast without building the ice table. How can we simplify this kind of concentration? Without an ice table, what are the concentrations of hydronium and hydroxide in a strong acid solution of this? So because of the strong acid solution, it means, so HA, it's completely displaced, so you have, this will be from here, this is 10 to the negative 3, this is 10 to the negative 3. You would say, well, actually there was already 10 to the negative 7. It's true, but I'm going to assume that it's so small, so this is just going to be 10 to the negative 3 molar. All right. Now, if the kW is 10 to the negative 14, and I already know that one of them is 10 to the negative 3, it means that my OH negative is 10 to the negative 14 divided by 10 to the negative 3, which is, not surprisingly, 10 to the negative 11 molar. Okay, so notice that from here, this is 10 to the negative 3, therefore this is 10 to the negative 11. Notice that the exponents, in this case, always add up to the constant of the autoionization of water. So in next video, we'll do the same for base, and hopefully everything will make more sense.